Volumes of revolution. I haven't looked at it. Well, that's good. And so, I need to explain what's going on here. Okay. Alright. Whoa, got a bowl. Okay. Might be wrong. This is the x-axis. Okay. This might be the y, actually. No, let's pretend this is the y. This is the z-axis. So this is 3 dimensions. So these are the functions that are graphed. Right? This is a y parabola. Right? Opens up because the x squared is positive. Am I recording?
Yeah.
And starts at 1/2. So that's a nice curve. And then this weird cosine thing looks like there's a vertical shrink by a factor of 1/2. The period is 2 pi over 7, right? But it follows this line negative x squared plus 3. I'm not sure why this is that, but anyway, you know, probably does a cosine thing. So if we look at the, I don't think they intersect. Anyway, if we look at the area between these two, it's like that. And if we revolve that area about the x-axis, it's a hard thing to think about. I mean, if I actually 2 pencils. If I had these 2 pencils glued together like this, right? And then this pencil had a little flag on it, the shape of this. And I spun it, right? This shape would like come out here and then go around and make a little donut. It's not really move. It's not really move either. Oh, this is the shape of it. Like that. Right? You see it? So that's what we're going to find the volume of. Today. We're taking an area between 2 curves, right? And you know it's just the top function minus the bottom function. And we're revolving that area around an axis of revolution. And we're going to find the volume of it. simple example. I might go up with the same example they have. If I take the function y equals x and the function y equals x squared, those two curves intersect at this point, 1 and 1, right? Right, if you plug in 1/2 for y equals x, the y value for this is 1/2. The y value of this 1/2 squared is 1/4. So it's lower, right? But anyway, look at this area. How would you find this area between the two curves? Top function minus the bottom function. And what's the integral?
0.
Okay. Now this is important. We look at the rectangle in the sketch of the graph, and rectangles move side to side. Rectangles are perpendicular to the x-axis, so we're going to use x values for your integral. And the smallest x value is the x value to the furthest left of the shaded area, 0. And then if you take the shaded area all the way to this end, the x value at this end is 1. So this rectangle moves side to side to get that total area. And we get x squared over 2 minus x to the third over 3. 0 to 1 is 1/2 minus 1/3, which is 1/6. And there's the area. Okay. We can use that same logic to find the volume of the solid generated when revolving this shaded area about, any axis. But for now, since I'm just showing you how to do it, we'll go about the x-axis. So like if we revolve this around like the reflection is this shape, but there would also be like, it's revolving about, so like when the revolution stops here, there's a flat outside edge with like a curvy inside edge. It's kind of like a funnel with a flat, it comes to a point, so there's no hole in it. Right? And then the inside would just kind of be bowed in. But we still take this rectangle and revolve it around the x-axis. So if I took like one slice of this solid out, hold it out, what shape would it be? If I took this slice out, and we've got this solid here. If I took a slice out, what would the shape be? It wouldn't be a triangle. Yeah, let's make it easier. Y equals the square of x. Let's just find this area. From 0 to 4. And revolve this area around the x-axis. Okay? So then its reflection would be here. And actually, there would be, this edge would be like this. And then this would be a flat surface here. So it'd be kind of like half of a football, but it's a solid. Right? Do you see that? If I took this rectangle, this arbitrary rectangle in the middle of the shaded area, and it revolves about the x-axis, what shape is that?
Ellipse.
Well, this radius, all the way around, stays the same.
Circle.
Yeah, it would be a circle, right? If I took that slice out, it would be a circle. So to find this volume, what actually all you do is you integrate the area of a circle, the area of the cross section. The circle's area is just pi r squared. Since rectangles are perpendicular to the x-axis, it's dx. Okay? What's the height of this rectangle? It's, well, this point is the point x coming y. And the x is like how far into the shaded area it is, and the y is the length of that rectangle.
Square root of x.
Yeah, y equals the square root of x, so this is the square root of x. What about the integral? If this rectangle goes all the way to the left, how far can it go? If this rectangle goes all the way to the right, how far can it go?
0 to 4.
0 to 4. We integrate this, we get, this is x, or x squared over 2, 0 to 4 times pi. And you get 8 minus 0, so we get 8 pi. Okay? So that cross section is a circle. So we use something called the disk method. So we just integrate pi r squared. And the pi is a constant, so it can come out. And the function, the radius changes depending on where you are in the shaded area. So we need to use a variable for that, so we're using the square root of x. Because it varies, right? As x starts at 1 and goes to 4. Let's look at this again. Notice that the shaded area does not border the axis of revolution. So if we take this little thing and spun it on the x-axis, it would make a solid. The outside of the solid would be like a cone, but the inside of the solid would be like a funnel. There would be a hole in it, right? This whole thing. If I took out a slice, what shape would it be?
Circle.
The outside would be a circle, but there'd be a hole in the middle of it. So that's like two concentric circles. Be like a washer, right? It would be like a washer. It'd be a circle with a hole. Okay? And if you get this situation where the shaded area does not border the axis of revolution, then we would have to use the washer method. As opposed to the disk method. The disk method, we're integrating pi r squared. The washer method, we integrate, well, if we're going to find the area of this cross section, there are two different radii. Like the big circle has a radius and the small circle has a radius. And the way you find the part of the solid, that's between these two, is you find the area of the big circle and subtract the area of the central circle, right? So the washer method is we're integrating pi capital R squared minus little r squared. We're finding the area of the solid. If the outside were just the whole thing, then we'd subtract the area of the inside, the part that's not there, right? Where this is capital R and that's little r. And that looks like this, right? It's pi integral something squared minus something else squared. So let's do this. Right? What's the outside? What's the outside radius? if this is the point right here, it's the point x comma y. This curve is y equals x. What's this distance right here? This distance, x. It's y, but we have to be in terms of x. And then the inside radius is this distance. This distance, from here to here. This point right here is x comma y, but the y this time is in y equals x, the y this time is y equals x squared. So what is this distance? X or y value? X squared. Squared. How about the interval? One, you look at the x-axis for the interval, and that's how to do this. We need grouping symbols since it's a sum. So we have x squared minus x to the fourth. Times pi. That's x to the third. Over 3 minus x to the 5 over 5. And we get 1/3 minus 1/5. 2/15. Yeah, 2/15. Any questions? Okay, so let's do the examples they have for us. We're not doing this. This is so we have this curve. Let's just grab it and see what it looks like. It looks like cosine. Period, cosine, or the amplitude changes, it keeps getting bigger. Yeah, let's see what it looks like in the graphic. Not now, I'm working. X cosine of x. Make sure you're in radian mode. Oh, this thing is so terrible. I'm just checking that one to see if it's normal. It's pretty normal. So we're going from -2 to 2, is that what it said?
Yeah.
Here we go. Here's the graph. We're going to revolve this about the x-axis. Rectangles perpendicular to the x-axis. So, what do I do?
Let's see. Interval 2 plus x minus.
From function.
Is it the first have to have a polygon square as well?
If we were revolving it, we would,
Or not?
oh, we are revolving. So then the wait, what? And its reflection is there, so it's that now. So we integrate pi r squared. We can't integrate x cosine of x. I don't want to. So why don't you grab your calculator for this answer? So I would, out of here, just press 9. It's -2 to 2. I can do pi y1 squared dx. I can integrate when it's square. No, I can integrate x cosine of x by using something we'll learn after your AP exam. Integration by parts. 4288. Volume equals. Is it 42.5288?
52
4288. Everybody good? I don't know why that's the first one we're doing. In the first reasoning closed by the y-axis in the graphs of y equals cosine of x, y equals sine of x, revolved about the x-axis to form a solid. So, sine looks like, cosine looks like this, sine looks like that. So this is the area, this is the shaded area. Do you know what theta value gives you the same, where do these intersect? Same y values. One is, the y value one is there. The x value of 1 is like pi over 4. Yeah, pi over 4, the sine is the square root of 2, cosine is the square root of 2 over 2. So this shaded area perpendicular to the x-axis looks like that. Okay, so how am I going to use, or how are we going to find this volume revolved about the x-axis? We're going to use the washer method, or the shell method, or the disk method. Does the shaded part order the axis of revolution over the whole interval? Does not. So we cannot use the disk method. We have to use the washer method. Washer, remember, is interval,
0 to pi 4.
0 to pi over 4. Big radius,
Cosine.
cosine x. And the small radius, yes, this distance is sine of x, because that's the function it goes to. The distance is cosine of x. It's too bad it's not plus. We just integrate 1, easiest thing ever. I don't know how to integrate cosine squared x. Unless we use the trigonometric identities, power reducing identity or half angle identities, which
No.
I can do. You don't have to. So use your calculator to figure this out. Okay. Did you get that?
Yeah.
1.5708. That's the best answer I can find. You have choices though. The Purell smells good. Doesn't hurt your hands. Any questions about this? There will be problems where you actually have to do the integrating. You want to try this? Oh, shells. Why don't you try this using not shells, using the washer or discard? Shells is a thing, but I'm not teaching you. Did we already do this one? Yeah, we did. Square root of x, under the square root of x from 0 to 4. That was this. this is not so bad. Why don't we do this one though from around the x-axis, not the y-axis. X equals 0 is the y-axis. So would you guys sketch that area? Would you be able to sketch it? What does this look like? We're not going about the y-axis, we're going about the x-axis. Because this is another shells question. We're not doing shells. You guys know what it looks like?
Isn't that a semicircle?
What's that?
Isn't the first one a semicircle?
First is a parabola, opens down, crosses the x-axis at 2. It would be a circle if it were the square root of 4 minus x squared. 4 minus x squared, correct. Y equals x is a line, y equals x. So they do intersect in a spot. Where do they intersect? It does not look like they intersect. Nice. So let's graph my calculator, see where they intersect. Oh, I really wanted to do it with my hands. Nice. One point 5615528. Did you guys see how I got it? Graph them both, see where they intersect. Now, since x equals this number, that's the number we need, I'm going to press x. There's the actual number. And I'm going to store that into a, just so I have it, in case I need it. Did you see how I did that? 1, 5, 6, 1, 5. Okay. So here's the area. So what do I integrate? What's my integral? We're revolving this about the x-axis. It's dx because the rectangles are perpendicular to the x-axis.
4 minus x squared, and then
Top function, 4 minus x squared, minus the bottom function, x. Integral, 0 to what number?
2.
Intersection point. I'm going to say 0 to a, because I saved this number in a. Okay, are you good? Now you use your calculator to find that area. Like if you had to find this area by hand, like say they intersected at 2, or something nice. We could do it, but you'd have to FOIL out the 4 minus x squared. You get 16 minus 8x squared plus x to the 4th. Minus x squared, anyway. And then you can integrate it. Anyway, we use our calculator. Pi integral 0 to a y1 squared minus y2 squared dx. Get that? 4388? 48.4388?
Yeah.
Any questions? And y1 I just had 4 minus x squared, and y2 just had x. Any questions? You guys see how this relates to, like on that quiz where you had to find the area of R? So we'll find the area of R and then we'll revolve R around an axis of revolution. Or, something else. I'll teach you later. I already did. Yeah. This is a integration. Find the volume when you know the shape of the cross section. So this paperweight, we shape the region between the x-axis and one arch of curve y equals 2 sine inverse. 1, I guess from 0 to pi over 2, goes up to 2. And this, the base of the weight is this. And the rectangles still go from 0 to pi over 2, perpendicular to the x-axis. But this is the base of the weight, and each cross-section perpendicular to the x-axis is like half of a circle. Anyway. All the homework does not have